Regular hexagon ABCDEF has an area of 24 square units. Okay, so here's our hexagon here. And we know it's 24 square units. M and N are the midpoints of AF and CD. Alright, so here's M, which is the midpoint of AF, and N, which is the midpoint of CD. If MP is parallel to AB, alright, let's mark that. So here's MP, and it's parallel to AB. MO is parallel to EF, alright, so here's MO, and I'll mark it with a little different hash marks. It's parallel to EF, okay. PN is parallel to BC. Okay, so here's PN and BC. Now, one thing, in a hexagon, we have three sets of parallel sides. Okay, so BC and EF are parallel. Alright, and so if EF is parallel to BC and BC is parallel to PN, then all of these four sides, MO, FE, PN, and BC are all parallel. So I'm going to actually use the same hash marks here. Alright, so those are all parallel to each other. And also, here AB is parallel to DE, okay? And we're told that ON and ED are parallel, so these lines are also parallel, okay? So the set of these four lines. So we have AB, MP, ON, and ED. Those are all parallel to each other. Alright? So, and we're asked to find the area of the rhombus MNO, MNOP, or MPNO, I guess in this case is what it says, MPNO, right here. So this middle four-sided figure here. Alright, well, a couple things about a regular hexagon that are good to know. One is that the interior angles are all 120 degrees. Okay, and if you forget that, I mean, you might just remember that, but if you forget that, one thing you can do with polygons, if you draw, here's a hexagon, and I can break that hexagon up into 4 triangles. Oops, that should go to the corner, but it doesn't quite. But anyway, so these are 4 triangles. So, and each of the triangles has 180 degrees. That's pretty easy to remember because you probably learned it when you were pretty young. So the total of all of the interior angles of this hexagon has to be 180 times 4. Okay, so that's 720. And so that means that each interior angle, since it's a regular one, they're all equal. So if we divide it by 6, we get 120 degrees. Okay, so if you forget, then you can always figure out the interior angles of a polygon just using this reasoning. Okay, so if I actually draw a line through here, dividing this into 2 halves because it's symmetrical on each side here, you can see that this whole angle had to be 120 degrees. This angle B here had to be 120 degrees, and so if we divide it in half and everything's symmetrical, then this is 60 degrees and this is 60 degrees. Okay, and another thing about a hexagon, let me draw another hexagon. I can tell already I'm off here, but you'll get the idea. Alright, so here's a hexagon. Let's pretend it's regular. And if I divide it in half all different ways, it's symmetrical along 3 different lines of symmetry here. Actually more than that, but we can connect the vertices, and it's symmetrical along all those diagonals. So, and this is 60 degrees, and so this is 60 degrees, this is 60 degrees. So these are all equilateral triangles, okay? And and they're all congruent to each other. So if the whole hexagon is 24 square units, and we can break it up into 6 triangles, 6 equilateral triangles, then each one of these equilateral triangles is 4 units. 4 square units, I should say. Okay? Makes sense? Alright, let's go back to our figure here, because you can see here we have these parallel lines, and if I look at these parallel lines, AB and PM, okay, and you can see that the corresponding angle to this 60-degree angle is this, so this has to be 60 degrees, because corresponding angles of parallel lines are equal, okay? So here's our two parallel lines, and let's say this is the transversal of those two parallel lines, okay? This line that I drew across the center, that's our transversal, so this has to be 60 degrees. And also, this has to be 60 degrees, and again, this is, again, the corresponding angle of these two parallel lines and this transversal, okay? You see that? And we can actually do the same thing over here if we look at these two parallel lines, okay? These two and the transversal here, okay? Yeah, actually, let me, you know, I could draw another diagonal across here, which would divide it into 2 halves again. This would be 60, and this would be 60, and this would be 62, and this would be 60, well, 60 also, and this would be 60, okay? So you can see what we've got here in the middle is our middle here is another equilateral triangle. So this has to be 60. So this rhombus in the center is actually made up of 2 equilateral triangles, and those 2 equilateral triangles, if I were to draw in all the diagonals, let me see if I can make them look diagonal. So this essentially is this. So each of these equilateral triangles is 4, and you can see this is 4, and the height here of this triangle is the same as the height of this triangle that's half of the rhombus, okay? So you can see that these equilateral triangles that make up the rhombus are congruent to the equilateral triangles that make up the whole hexagon, okay? So if each one of these is 4 and these 2 are congruent, then the rhombus has to have a area of 8 square units.